Yeah, in this lecture, we will first give a summary of all the um, rules that we have, and we will also take an example on using the rules uh, um, one by one. We'll see how we can do this. We'll have the repeat until block in that, and we'll see how to use those proof rules. So, to summarize, summary of proof rules. We have the following. The first one was what we call the consequence rule. Had two forms. P R P S R R implies Q, then we can conclude that P S. First, let me call it A, and here another form B, and P implies Q R S Q. And we have again P E S. What do these rules essentially say? That if P is known to be a precondition for R, and the assertion R implies the assertion Q, then P is a precondition for the for S, and which from which you can assert that the precondition Q, postcondition Q will be true. In the other case, R is known to be the precondition for S, and the postcondition is Q, then any, sorry, should be corrected here, any precondition that implies R is also the precondition for S, and um, the proof rule states that we can infer that Q will be true. Then we looked at the null statement rule. This is for various types of statements, and the null statement rule was essentially P, and whether null is semicolon or escape or whatever, is also the precondition and postcondition. Postcondition is the same as the precondition. Then we looked at the assignment rule. This is a very important rule because it's a fundamental building block of most programs. And assignment rule states that if P is known to be true for an expression E before the application of the assignment, and then you have X is assigned the value of E, then the precondition is still true after the truth about the expression does not change even after the assignment statement. Why is this useful for us? When a variable is assigned, for example, to an expression, you can infer what the value of the variable will be. Then we did what is called the compound or the composite rule, and this was essentially, it said that Pi minus 1 Si Pi for I equals 1, 2, dot, 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 n statements, then we can say P naught S1 S2 to Sn. You can infer Pn given this. Okay, that's what it says. What it says is if Pi minus 1 is a precondition for Si and Pi is the postcondition, then we can infer that P naught is the precondition for the entire sequence of statements and Pn is the postcondition. Then we did something called the conditional rule, and the conditional rule is primarily for the useful for the alternative statement in a program. And what this states is that P and B S1 Q comma P and not B S2 Q, then we can infer that P if B, then S1 else S2 and Q. P will be the precondition for the if then else statement. Again, in the conditional statement, there are two forms. Then we have P and B S Q and comma P not B implies not B implies Q, then we can infer that P if B then S. This is a kind of an alternative statement which does not have an else. I just want to point out there are alternative statements of this kind. If B1, then if B2, then else, if B1, then B2, then S1, else S2, statements of this kind. The else is always associated. This is written as if B1, then if B2, S1, else S2, then the if is always associated with the the else is always associated with the most recent if. So this else goes along with this if, and that's how you treat the statement. This statement is also known as what we call the dangling else problem. In the alternative form, we had a case 3, which was the case statement, case rule, and here what we said was P and X equals the I, Si, Q, I equals 1, 2, N, then P and X belonging to K1, K2, Kn, case X of K1, S1, K2, S2, Kn, Sn, Q. That is, we can infer the that if X belongs to one of these values, K1 to Kn, and P is true at the beginning, and if one of these conditions are satisfied, then we can infer that the post condition Q will be true. This is called the case rule. Then we had the while do rule, and basically this statement P and B S. P, what is P now? P is your loop invariant. Then P while B do S P and not D. Okay. So basically the P is a loop invariant that is always true. Li loop invariant always true before entry into the loop, at the end of the execution of the loop, and when you exit the loop. Then what we did was the next statement was the compound rule, conditional rule. So these were for the repetitive statements. Let me call this A here. 6B was the repeat until statement, and we proved the repeat until statement using the while rule. And what does it say? P is the precondition, S is a sequence of statements that is part of the, notice that this one is the first execution of the loop, and Q and not B implies P, then we can infer P repeat S until B, and we can infer that Q and not B. Q and B is true. Okay. Q and not P implies P. Notice that the statement is executed first, then this implies this. Get into the loop, and then you can repeat. And we saw that proof for repeat until was through the while proof. How did we do this? We made an equivalence of repeat and while and proofs. Okay. Now what I'm going to do is I'm going to take one example using the basic proof rules. And what I'm going to take here is I'm going to take this example of multiplication by repeated addition. Okay. And let's do this. So you start with two variables. Maybe it's good to define. Anyway, let's start with two variables. All the variables here, I think you have. Okay, let me define the variables first. I have int x comma y, the two numbers that you have to multiply, and some temporary variables z comma u. Let's see how we go about doing this. Start with x greater than 0 and y greater than 0 is a precondition before the program starts. Then we have z is assigned the value of 0, u is assigned the value of x, and we repeat the statement. Repeat z equals, z is assigned the value of z plus y, u is assigned the value of u minus 1 until u becomes 0. So what have we done here? We are basically x times the value of y is going to be added. Okay, that's what we're trying to do. And what do we infer at the end of this repeat until block? We can infer that z is equal to x star y. Can be inferred. So let's draw this. We have A over here, and let's call this point A, and we have x greater than 0 and y greater than 0. If it's not, you just make it, take the absolute value and multiply and attach the sign. Z is assigned to 0, u is assigned to x, our first statement. And what is the rule that we will use here? We will use to prove this, the post condition after this. Let me call this a point B over here. And we will use the rules of composition to prove the post condition. And what is the post condition that we have here? We have z plus u star y equals x star y, and u greater than 0. That is what we start with as the condition over here. Why so? Because z equal to u z plus u star y equal to x star y. Why is that correct? Because z is accumulating the values of y, and what u is being decremented by y. Therefore, if you take the content of z at any point and u star y, it should be x star y, and u is greater than 0. Then we come to the repeat block. What do we do in the repeat block? We have z equals, z is assigned the value of z plus y, u is assigned the value of u minus 1. And then we reach this point C over here. And what do we have over here? We have z plus, again, still z plus u star y equals x star y, and u greater than or equal to 0, because u is being decremented. That's the only difference that we are going to see. What are we seeing here? We are seeing here x star z plus u star y equals, what are we seeing here? We are seeing, I'm just correcting these things, z plus u star y equal to x star y, but u greater than or equal to 0. And where does it come from? Again, you apply the consequence rules. Given that this is the precondition, u greater than 0, this condition is satisfied. What do you see here with this assignment statement? The value of z remains, when you're looking at the assignment statement, whatever is true about z and y before still continues to be true. And then you are decrementing u, therefore u becomes greater than or equal to 0. Okay. Then this is the point C that we have. And at this point C, cramped, u equal to 0, then if it is true, we exit, and if it is false, we repeat and go back to B again. Okay, that's what we're doing. True here, and at D, let me call this point B, what can we say? At this point B, we can say that z plus u star y equals x star y and u equal to 0. And at the end of it, what can you say? Because u becomes equal to 0, at this point E, we can say z equals x star y. Okay, so this completes the proof rule for use of the various basics proof rules. What all did we use? We used the assignment proof rule. Again, the assignment proof rule, given that this is the precondition. Notice that we are entering the loop. This is a repeat until block. Therefore, the S statement gets executed at least once. Then we proved what C was over here. And once we prove what C is over here, then we want to go back to the beginning again over here. And then B should be satisfied again because U is not equal to 0. Then U is still greater than 0. Condition B is satisfied. Repeat through the loop. When U becomes 0, notice that Z plus U star Y equals X star Y and U equal to 0. And finally, at this point, when it exits the loop, because U is 0 from here, this implies that Z is equal to X star Y. So this completes an example